Hello, learners. Welcome to yet another lesson. I am your teacher, Madam Alice, and we are still looking at the Form 3 chemistry. We are looking at the second chapter, the mole, and today's lesson we are looking at the stoichiometry equations and also the ionic equations. Okay, welcome. So this is our part 8 of the topic or the chapter, the mole. And we start looking at what are stoichiometry equations. So stoichiometry equation is an equation whose reactants and the products are in whole numbers. So the mole that of the reactants and the products should be in whole numbers. So if it is in fraction, that simply is not a stoichiometric equation. We have an example there of such kind of equations where we are reacting magnesium and oxygen, or we are burning magnesium in presence of oxygen to get magnesium oxide. So from balancing that chemical equation, we can see that 2 moles of magnesium are reacting with 1 mole of oxygen to give us 2 moles of magnesium oxide. So in the above reaction, the proportions in which the reactants are magnesium and oxygen, and the product, that is the magnesium oxide, reacts in terms of moles. And this, we call it the mole ratios. So the mole ratio is the mole ratio of the reactants to products is 2:1:2, meaning 2 moles of magnesium are burnt completely in presence of 1 mole of oxygen gas to form 2 moles of magnesium oxide. Okay, so that is an example of a stoichiometry equation. As long as you can write a correct chemical equation with the correct chemical symbols and the correct balancing, then as long as that chemical equation has mole ratio that is in whole numbers, we call it a stoichiometry equation. Another example is when we are reacting magnesium and nitrogen. So this gives us magnesium nitride. So the reactants, 3 moles of magnesium are reacting with 1 mole of nitrogen to give us 1 mole of magnesium nitride. So the mole ratio there will be 3:1:1. So that is also another example of a stoichiometry equation. Now we say that for us to have correctly written stoichiometry equation, the following should be considered. 1, the equation must be correctly balanced. Okay, it must contain the correct symbols and also the correct reactants and products. So make sure the reactants are giving the correct products. Okay, now let us look at ionic equations. What are ionic equations? So before looking at ionic equations, we look at the term ionic compounds. And ionic compounds, these are compounds that are formed by the electrostatic attraction between positively and negatively charged ions. So when these cations and anions attract and come together, they form ionic compounds. Then we can define what are ionic equations, and we say an ionic equation is a chemical equation that only includes the species that are involved in chemical reactions as ions. So this is what we say or we refer to as ionic equations, a chemical equation that includes the species that are involved in chemical reactions as ions. So those are ionic equations. Okay, another term we are going to define is a complete ionic equation. What is a complete ionic equation? So this is an equation that shows all ions in a chemical reactions as ions. So as we write the ionic equation, we have first write the complete ionic equation. So the complete ionic equations shows all the ions that are taking place in a chemical reactions. Okay, the fourth term is the net ionic equation. The net ionic equation is an equation that shows only the ions that participate in a reaction, excluding the spectator ions. So we are going to see what are spectator ions. These are ions that do not change in the reactant side and in the product side, meaning that they are not involved in formation of that compound. So now we look at the example. The first example we are going to look at is a precipitation reaction, and this is a reaction between silver nitrate and sodium chloride. So first of all is to write the chemical equation itself. Make sure the chemical equation is correctly balanced. That's the first thing. It is correctly written with the correct symbols, and also the state symbols are included. So in our case, we are reacting silver nitrate. It is in aqueous form, or it is in solution. So it is in aqueous state. Then we are reacting it with sodium chloride. It also in aqueous. It is in solution to give us. So what are the products? Silver chloride, which is a solid, and also sodium nitrate. So silver chloride and sodium nitrate are our products. Now, second step is to write a complete ionic equation. That is, we split these ions but include all of them in that equation. So the first one here, you can see we can split this one because any solution that its state symbol is aqueous can be split. So we have silver ions, they are positively charged ions. Then we have nitrate ions, they are negatively charged. We have sodium ions, positively charged, that's why we are using that plus, and chlorine ions. So those ions on the left side are our reactants, and they can all be split since they are in aqueous state. Let's move to the right hand side where we have the products. So we have silver chloride. Silver chloride is a solid, so we don't split. It cannot be split. Okay, so what we are going to split on the right hand side is the sodium nitrate. So the sodium nitrate, since it's in aqueous state, it is giving us, or it is dissolving to give us sodium ions and nitrate ions. So those are what we have. Now we need to see or to get which are the spectator ions. These are ions that does not take place. They don't change whether they were in aqueous. They will be in aqueous in reactant side and in product side. So these are the ions we are calling the spectator ions. So we can just cancel them. Let's find them. So in our complete ionic equation here, we have the first one. You can begin by looking at silver. Silver was in aqueous state. On the product side, it is solid. So that one is changing, meaning it is taking part in formation of silver chloride. Then we have nitrate ions. It is in aqueous, and also in the product side it is in aqueous. So that one is a spectator, and so we can just cross them. You can just put a line like that. Let's look at sodium. Sodium ions were in aqueous state. On the product side, sodium ions are in aqueous, meaning it has not changed. So it is also a what? It is also a spectator ion. So we cancel the sodium ions on both sides. So now we are left with chlorine. Chlorine was in aqueous state. On the product side, it is in solid state, meaning chlorine ions has been used or has taken place in formation of the silver chloride. So now the net ionic equation, we said is an equation showing the ions that participate. So we drop the spectator ions, or those ions that does not participate. So we only include the ions that are participating in that formation of silver chloride. So we have silver ions and chlorine ions to give us silver chloride. Okay, so this is the net ionic equation and the ionic equation that we are required to give. So if we are told to write the ionic equation for the precipitation reaction or the reaction between silver nitrate and sodium chloride, that is what you will give. The sodium and nitrate ions are spectator ions, so they do not participate in the formation of the solid, that is the silver chloride. So we do not write them, or we do not include them while writing the ionic equation. Example 2, we are looking at a neutralization reaction. A neutralization reaction is the reaction between an acid and a base. So neutralization reaction, a reaction between an acid and a base to give us two products, that is salt and water. So in our case here, we are having hydrochloric acid and sodium hydroxide reacting. So hydrochloric acid is in aqueous state and sodium hydroxide also in aqueous state. To give us sodium chloride will be the salt, it is in aqueous, plus water, right? So water is in liquid, will be in liquid. So that will be the reaction, that is the complete chemical reaction. So now we need to get the complete ionic equation. We split these ions. So in hydrochloric acid, we have hydrogen ions and chlorine ions. In sodium hydroxide, we can split it. It will dissolve to give us sodium ions and hydroxide ions. Then product side, we have sodium ions, chlorine ions, and also we have water. So water is in liquid state, not in aqueous. So it does not split. The ions cannot split since it is in liquid state. Now, we are going to get those ions that are taking or are not participating in formation of water. Those are the spectator ions, and these are the ions that does not change their state symbols. For example, we have hydrogen aqueous. Hydrogen is in liquid, so hydrogen is taking place. Then we have chlorine ions, aqueous, chlorine ion, aqueous. So those are spectator ions. So we just cross them. We cross them like that. Another spectator ion is the sodium ion. It is in aqueous, meaning it does not take place in, or it does not participate in the formation of water. So now to get the net ionic equation, we just pick those ions that are left. We have now hydrogen ions to react with hydroxide ions to give us water. And this is the net ionic equation that we are required to write for the reaction between hydrochloric acid and sodium hydroxide. So we say the sodium and chloride ions are spectator ions and do not participate in the formation of water. Only the hydrogen and hydroxide ions react to form water. Okay, that is just to show you how you write the ionic equations and what are ionic equations. So it is very simple when you follow those steps. You just write the chemical equation with the correct state symbols, then split the ionic equation or the chemical equations in ions. Now, the ions present in those in the chemical equation, then just cancel out the spectator ions and write an equation between the other ions that are left. So this gives us the net ionic equation. That marks the end of part 8 and also the end of this lesson. So let us meet again in our next lesson. That will be part 9. Have a nice time.